Hi, I've been seeing a lot of questions on the forums about how to drive a fairly high load using a microcontroller. It doesn't matter whether it's a Texas Instruments MSP430 running at 3.3 volts or whether it's an Arduino based micro running at 5 volts. The question still remains, if you want to drive something more than just a little LED, how do you do it? And I've seen a lot of variations of what people suggest. And well, to be honest, some of them will work fine, but some of them really you're just trying to overload the microcontroller and potentially cause problems. I've actually seen people connecting motors directly to an Arduino, for instance, trying to drive it. Now if you have a really small one, maybe that'll work to a certain extent, but you are risking actually doing damage to the microcontroller because it has back EMFs when you stop driving it, and those can generate a lot of volts out of the motor and can actually damage the microcontroller input-output ports. So given that, how do you do this? What I'm going to do here is show you first of all how to increase the drive capability when you don't need to have the output isolated. So you're not trying to drive mains, you're not trying to drive high-powered, high-voltage loads or have big cable runs that might cause issues for the microcontroller. Right? This is straightforward. I have a motor, I have a relay, or some high-powered LEDs, maybe 50 watts or something like that, and you don't need to isolate from the microcontroller. So what's the first thing you have to think about? Well, what is the output of a microcontroller? How much current can it deliver and at what voltage? So if I just step back here a little bit, here's my typical microcontroller. Like I said, it doesn't really matter which one it is, but it's either going to be running at 5 volts or it's going to be running at 3.3 volts. Now these are the two typical voltages. There are other ones that run at different voltages to this, but it's unlikely most of you will ever come across them. So that means that the output, and I've just drawn one pin here for the output, can go from 0 volts up to 5.0 volts, or it can go up to 3.3 volts. So you need to know how much current can actually come out of that microcontroller. Typically, for almost every single one I've come across, they recommend no more than about 10 milliamps and as much as maybe 20, but that's hitting the absolute max rating if you look at the data sheets for a lot of these microcontrollers. So that's not really a lot to do anything. Yes, you can drive a small LED with it, it's perfectly fine for that, but beyond that, it really doesn't work for anything. Not without risking damaging or overheating the chip. So you need to amplify the current. Right? We don't necessarily need to amplify the voltage, but you can also do that depending on what load you've got. But you definitely need to increase the current capability. You do this by using some kind of transistor in the easiest form. Now, it can be a field effect transistor, which is one of the relatively newer technologies, although I think it was actually invented before the standard bipolar transistor that's around these days that everybody uses. Anyway, I'll deal with the transistor first, and then we'll go on to how you would use a field effect transistor as well. So I've got two circuits here. I'm going to ignore the red one for now. Let's just look at this black one here that I've attached. So we have a transistor. I picked one that a lot of people use. It's a 2N2222 transistor, and what its capabilities are is it has an absolute max voltage across the collector to the emitter of 40 volts, and you can put about a half an amp through it. Right? That's enough to deal with a lot of relays, relatively low powered LEDs up to maybe 1 to maybe 5 watts. Beyond that, it's really not going to be able to handle it. But the thing that a lot of people don't know about transistors is they have a gain. Now that gain is termed as HFE when you look at the data sheets, but it really means that for a given current going into the transistor, how much current will it allow to flow between the collector and the emitter? And that is relative to what load you put on it. So in our case, a relay, for instance, might want to consume 150 milliamps to energize it. So if you want to have 150 milliamps here, you need to put enough current through the base emitter junction of this transistor in order that by the time you multiply it by the gain, you can have your 150 milliamps flowing through here, or more. The harder you turn this transistor on, the lower the voltage drop on the transistor between the collector and the emitter. And why do you want it to have a low voltage drop between the collector and the emitter? Because it's power, it's heat that comes out of the transistor. And we all know from Ohm's law that watts is amps times volts. So if you've got 100 milliamps going across here and you have 1 volt drop, then you have 100 milliwatts. But if you have 2 volts dropped across here, that's 200 milliwatts. That's about a quarter of a watt, and this transistor is going to start getting warm. Okay. Now the transistor, I've actually written down some of the other specs here. For this 2N2222, it's typically got a gain at 150 milliamps, because it does depend on how much current you're putting through it, of about 75. That means that if you put 1 milliamp in the base to the emitter, you will get 75 milliamps flowing between the collector and the emitter. Now, there's no guarantees you'll get that. It all depends on what load you've put up here. But it will allow you to put up to that much load. So if you put, say, a 10 ohm resistor up here that could allow at 5 volts, that would be 500 milliamps to flow through, then you won't get 500 milliamps flowing through it. You'll get the 75 milliamps if you've only got 1 milliamp here, because that's the gain. But now you're working this transistor in its linear region. It's not turned fully on, and it's going to be dissipating a lot of power across it. And if you do the math with 75 milliamps flowing through here, you'll be able to figure it out. I'm not going to go into it right now because I don't want to deal with the analog side of things. I'm just going to try and deal with the fact that we want to use these as switches. So I put some values here. If you have this R of 10 ohms, then with a 5 volt input with 10 ohms, you're going to get 500 milliamps flowing through that resistor and through the base emitter. Now obviously if you've got a gain of 75, that's going to give you a huge amount of potential current, way more than this transistor could handle. If you used a 100 ohm resistor, it's 50 milliamps. Now we're talking about the right kind of ballpark. A 1K resistor will give you 5 milliamps. And if that's got a gain of 75, then that's probably around about 400-ish milliamps. I'm just flying the numbers off the top of my head here. So 75 times 5, okay, it's going to be plenty enough to drive your load, and it's going to be saturated. Now, why do you need the resistor between the base and the emitter? In the base. What it does is it limits the current that flows through the base emitter junction. This, to all intents and purposes, is just simply a diode. The arrow points in the direction that the power is going to flow through the transistor. So because it's a diode, it's only going to have a maximum voltage drop across it of about 0.6 volts. If you connect a 3.3 or a 5 volt output from a microcontroller straight to this without a resistor, it's going to pull this output right down to the 0.6 volt of the diode drop, and you're going to pull a very large amount of current out of your microcontroller, which is no good. You'll probably damage it. At a minimum, it's going to heat it up and make it fail. So you need a resistor to limit the current. Right? So let's just say we put a 1K resistor in here, and we've got about a 50 milliamp low current now flowing through the base emitter junction. So 5 milliamps here, you're going to have about 400 milliamps flowing through here. It's going to be turned pretty well on. If you have a load here that only requires 5 volts at 150 milliamps, like a relay, then this is going to have less than a volt drop between the collector and the emitter, and it's going to work pretty good. Alright, and it's going to turn hard on because you're actually asking for it to deliver more current than what it's capable of delivering based on the gain and the load. Therefore the volts is going to be all across the load. Now if you have an inductive load, you need to put a diode in the form shown here to protect the back EMF, because if you don't, what's going to happen is this voltage here is going to spike above the power rail and it's going to damage something. So this diode basically provides almost a short circuit. It limits the voltage, the reverse voltage, to 0.6 volts as it feeds back through because of the voltage drop of the diode. You can put different diodes in to reduce that even further, but you don't have to. So given that you've got sorry, I actually wrote down the calculations earlier, I forgot. So given that you've got a gain of 75 and you want 150 milliamps for, say, a relay, then you only actually have to pass through 2 milliamps in the base emitter with that gain to get your 150 milliamps, because it's 150 divided by the 75. So 2 milliamps, well, I'm just looking at this table, we've got half a milliamp with a 10K, 1K would give you 5 milliamps, so you could probably get away with about a 2.5K resistor and it would work. Putting a 1K in means you're really forcing the transistor into saturation, because your load is not going to allow any more current through, so your transistor is going to be turned high on and it's going to not have much power dissipation. So we're good to go with the transistor. So that circuit now, as simple as it is, it's just a resistor, a transistor, and then you put your load up here, will allow you to drive anything up to, with a 1K resistor here, up to probably the sort of 200-300 milliamp quite easily without too much of a problem. If you wanted to drive more up to the limit of the transistor, then drop your resistor down to maybe 100 ohms or 200 ohms in the base, and you're going to pretty much guarantee you're going to be keeping this transistor saturated for any load you put on it. But you need to make sure you don't put too much current flow through, because it will start getting hot. And of course, if you're trying to run in a low power situation with your microcontrollers, and maybe it's battery operated, then you really don't want to have too much current being drawn out of your microcontroller side of the circuitry. So you want to try and keep this high. So that's a transistor circuit, and it works for a lot of your basic operations. I'm just going to get an eraser here, and I'm just going to eliminate this off the board now, because we're done with it, and leave this second diagram. Now, I mentioned before that there's also FETs that you can use. These are field effect transistors, and there's a number of different kinds. But the one I'm going to talk about here today, is one very specific kind, which is an N-channel, ultra-powered MOSFET with a logic level input. And what it actually means is most FETs, you have to take the gate. They have a gate, a drain, and a source versus a base, emitter, and collector. Sorry, collector and emitter. And they're a voltage amplifier. Remember before we were talking about the transistor, they actually amplify current. By varying the load resistor and the base resistor, you're affecting the current, and the resistors are effectively changing that into a voltage for you. But the transistor itself works as a current amplifier. In the case of field effect transistors, these ones here, that's a symbol anyway for an N-channel field effect transistor. They're more of a voltage amplifier than a current amplifier. There is no direct connection. If you put a multimeter between the gate and the source, or the gate and the drain, you would find that the value is way up in the megohms, or even showing open circuit on your meter. So there is a capacitance there, maybe about 5 nanofarads or something like that, that you need to be aware of, especially when you're driving it from a microcontroller. But aside from that, it's basically just a voltage with a very, very high input impedance. Now, the reason I'm talking about a logic level FET is because if it wasn't a logic level one, this gate, in order to turn this on, would have to probably go up to maybe 10 volts before you would actually drive this FET into saturation, where you had very low power dissipated on the FET and all of your load was dropping the volts. And when you're not in the saturated mode, you're going to start dissipating a lot of heat in this FET. By using a logic level FET, the internal circuitry is actually designed such that the gate only has to go up to about 3.5–4 volts before the FET is fully turned on. It actually still behaves as a linear device, the same as a transistor does, and the same as all the other various types of FETs. It's just its input is designed to work within a lower voltage range. So why the resistor if it's open, basically an open high impedance load? Well, remember I mentioned the capacitance. So when this comes up, if you don't have a resistor to limit the current, you're actually going to draw quite a load of current through onto the gate while you charge up that capacitor. the capacitive effect of the gate source junction. So you put a resistor in here to just simply limit the amount of power. Now that resistor can be just a couple of hundred ohms or something. It doesn't have to be terribly big. Now you can make it bigger, but remember, with a resistor and a capacitor you have an RC time constant, and it will slow down how quickly this FET reacts to turning on when the input goes high before this becomes saturated. So if you're switching it at a lot of high frequencies, maybe because you're doing PWM to drive some dimming for some LEDs or something like that, you wouldn't want to have it taking too long to turn on, because your FET would be getting very warm while it goes through from being off into saturated in that linear region. So keep the value small, it'll switch on quickly, and it will then behave very nicely. Now the nice thing about this circuit is you've got a lot less current coming out of your microcontroller, but also a FET. One of the things I didn't mention before, let me just digress back to the transistor. This is the characteristics of the transistor. The volts between the collector and the emitter of a transistor. Alright, so the voltage between here and here is about 1 volt. So if you're putting 1 amp through this, that's 1 watt. That's a lot of power to get rid of. Now if you're driving something even more higher load, then you're going to have a heatsink on this. It's going to have to be a power transistor, and it's not going to be nice, because you're basically wasting all that energy. But if you're using a FET, what you get the benefit of, which I haven't mentioned yet, is that when these things turn on, they have a very, very low impedance between the drain and the source. Now for the one I was using, which is a 76137P, that's the part number, it has a capability of driving 75 amps between the drain and the source. It can have a maximum drain source voltage of 30 volts, so it's a little less volts than this one, but you can get ones for much higher voltages into the mains voltages, like 110, 220 volts. But typically, because of the power constraints, the currents are going to be a lot less. But this one will actually handle 75 amps at 30 volts. When it is fully turned on, when the gate is up at 10 volts, remember I said it turns on quicker and it's almost saturated at 4.5 volts. But when it goes to 10 volts, it actually only has 0.009 ohms across the drain and source. That's less resistance than the wires that you're probably connecting it up with. When you drive it with about 4.5 volts, so if you're doing it from an Arduino or something like that, then it has 0.014 ohms drop across the drain source. That's still very, very little, and if you do the math, you know, even if you're putting an amp through this thing, it's only 14 milliwatts, which is nothing. It's not even going to get warm. Even if you put 10 amps through it, it's still only going to be 140 milliwatts, so it might get a little bit warm, but it still probably won't even need a heatsink. So as you can see, compared to a transistor, this thing is great if you want to use it as a switch. And as you've seen, at low voltages, say you've got some 24 volt LED light strips for the kitchen or for a living room, and you've got a lot of them, you can easily get up into tens of amps of current that you want to switch. Now because you're isolated supply and everything else, you don't necessarily need to isolate that from the controller that's doing it, but you certainly need to have a transistor that is capable of controlling that high current. The previous circuit I had here with a regular transistor, you'd have to go to a power transistor in a large can, say like a 2N3055, and you'd have to have a heatsink on it because it's going to be dissipating quite a bit of heat. This FET, I've actually got one of these that I'm using in my kitchen. I don't have a heatsink. It's just put on the circuit board. It's just soldered straight in. It's sticking upright, so it's not even in contact with anything for the tab, and it doesn't even get warm. And it's driving probably 5 amps easily. So from a control perspective, you've got a microcontroller. If you've got an Arduino which is putting out 5 volts because it's a 5 volt 80 mega 328 or something like that that's drawing it, then it's going to put it on and it's going to be getting about 14 milliohms, so 14 milliwatts per amp that you're putting through it. If you're using something like a Texas Instruments launchpad, which is only giving out 3.3 volts, then it's going to be a little bit higher, maybe 20 milliohms or something like that. But that means you're only still going to dissipate 20 milliwatts per amp that you put through this thing. So that's going to give you a huge amount of current carrying capability with very, very little circuitry. I mean, it's a single transistor. It's in a TO220 package, the one I use. In fact, I've got one here. 1 second. All right, there it is right there. That's all it is, one of those. And you don't even need a heatsink if you're using it in its switch mode, and even up to about 10 amps. You just put that on your board, make sure you got thick enough traces, but you do not need even a heatsink for it. Okay, so what we've got here, resistor, the field effect transistor. Now this Zener diode here, sorry, Schottky diode, it's built into the FET. It protects the FET from reverse EMFs and everything else, but it's actually built into the package. It's not external. I've still put a diode here on the load because you want to protect the load from the spikes and things as well anyway, from back EMF into your power supplies and various other things. So you've got basically just two components. Before we had a resistor and a transistor. It was limited to half an amp. Now we have the same resistor, slightly different transistor. In this case, it's a FET one. You'd be able to drive 10, 20 amps quite easily without having to have any additional circuitry. Up to 10 amps, probably wouldn't even put a heatsink on. If you're getting over 10 amps, but you're making sure that you're driving this from 5 volts, maybe you just clip on one of those small heat sinks that just sits right on the tab. You don't necessarily have to bolt onto a chassis or anything like that. And that's all there is to be able to drive this. So any microcontroller, like I said, Arduino Uno, a Texas Instruments launch pad, or anything like that, in this case, you could put, like I said, a couple of 100 ohm resistor to the gate. This thing is just standing up. You load anything up to about 10 amps. It'll easily handle like a 24 volt or 12 volt supply with a great big string of LEDs, or a reasonably sized servo stepper motor and things like that. You could also drive from this, although you'd probably more likely get into some kind of bridge circuit and use P channel as well as N channel FET, which is a different, I'll do that as a different video. But in this case, as far as how do you drive a high power load and have the minimal amount of components to do it, that's pretty much it. So anyway, that's all I have for that. I just wanted to show you very quickly, because part of one of the projects I'm doing, which is for the electronic referee for element 14 with Texas Instruments, is I need to turn on and off some industrial sensors that would go across the tennis court, and they run at 24 volts, so I couldn't obviously drive that directly. And because there are quite a long set of wires between the microcontroller and the sensors, there's a higher probability of getting magnetic interference from other power systems nearby, from just general interference, radios, cell phones, whatever. Anything that can be generating an magnetic field would get picked up in the wires, and I didn't want it to be backfeeding into the microcontroller. So I had to figure out how to do this. Now, I initially was thinking of using something like this. I actually ended up using a P-channel FET with a slightly different circuit, because I was also opto-isolating the output. So I'll do a separate video for that and how you do that. But if you just want to drive relays, small motors, or even reasonable sized motors, and you're not using them in a linear mode, I would highly recommend using these field effect transistors. You can pick them up from Element 14, you can pick them up from eBay. They're just like $1 or $2 each, and coupled with just a resistor, for the price of like $250, which is what, English money, just over £1, it can save you a huge amount of hassle. So anyway, that's it. Hope you enjoyed that. Hope it was useful, and I'll have another one soon.